My name is Caleb Stanford, and I'll be talking about DiffStream, differential output testing for stream processing programs. This is joint work with my co-authors at the University of Pennsylvania. Recent years have seen an increase in stream processing applications. These are applications where you have distributed streaming data arriving at many locations, and you need to make real-time decisions over those data streams. These applications have given rise to companies such as Databricks, Materialize, and AWS, and have resulted in the increasing popularity of distributed stream processing systems, or DSPS, such as Spark Streaming, Apache Flink, and Apache Storm. To provide a bit more context about the evolution of these systems, it dates back to batch processing systems, which are typically based on SQL or MapReduce. Batch processing systems are distributed and fault tolerant, and they provide high throughput, but they don't provide real-time low latency processing. And so what these systems do, Spark, Flink, and Storm, for example, is additionally offer low latency processing and stateful event-by-event processing. And so they're kind of the next generation in this evolution of data processing systems. Despite the popularity of distributed stream processing systems, achieving correct parallelization remains difficult and prone to errors. To respond to this fact, you could take a number of approaches. One approach is to try verification, and there's a lot of work in verification of distributed systems and protocols, but in general, it's not accessible to end users of these systems, but only to experts who design them. In addition, you could take the approach of, to be more accessible to end users, you could take the approach of testing. But testing is actually not very explored in the streaming setting, and in fact, the state of the art that's used in practice is just unit and integration testing, as has been shown by a recent survey. To address this gap, we propose DiffStream, a differential testing library for Flink. I'll talk briefly about 3 parts. The first being differential testing framework, where the paradigm that we adopt is that you have an input, you have 2 programs, for example, a sequential program and a parallel program, and then you want to test whether they're equivalent in some sense. The core technical challenge here is, given the 2 programs and a specification of the ordering requirements on the output, you want to design a matching algorithm that compares those streams for equivalence up to the ordering requirements. And then you reach a verdict as to whether they're equivalent or not. And finally, I'll talk a little bit about our implementation, which can be found here and is open source on GitHub. So let me provide an example of what can go wrong when you're programming in these systems and trying to parallelize. So consider a topic counting example. Here we have an input, which is a stream of a bunch of words, for example, taken from Twitter over time, such as startup, playoffs, Apache, senator, and so on. And the words come from 2 different regions, region 1 in yellow and region 2 in blue. And we also have user queries interspersed with those words. And what we want to do is we have a pre-trained model that gives the topic for each word, and we want to produce as output the most frequent topic per region since the last query. So we want to take all of the words in between two of these queries, total up, apply the pre-trained model to get a topic for each word, total up the topics, and then provide the most frequent topic for each region. And though this computation is straightforward to understand, it's not straightforward to parallelize. And the reason for this is really due to these query events in red, these barriers. And they're difficult to parallelize because they have to act as delimiters for words, and it's difficult to preserve that in parallelism. And what's worse, this is not only not straightforward to parallelize, this computation is not straightforward to test. For example, via something like unit testing. And the diagnosis of this, as we'll see in a second, is that the correct program is a combination of ordered and out-of-order data. And this will be key to designing our solution. So what happens if you, I don't have time to go into the details of what the computation to implement this actually looks like, but I can show you what happens if you try to parallelize it. So first of all, you can write a sequential solution, which is relatively straightforward and correct. So maybe the sequential output is giving you this list of topics: tech, sports, and tech. If you just the first attempt to parallelize, just the automatic parallel solution that will be given to you by Flink or any other system, is actually incorrect. It's just gives you the incorrect answer. For example, maybe politics instead of tech. Then you can put in more effort to try to design a correct parallel solution. And one such incorrect attempt and correct attempt are given here. So the incorrect attempt here turns out to be parallelizing incorrectly. And the evidence for this is rather subtle because the output is still the same as in the first one, tech, sports, and tech, but it's out of order. So the blue events, these are for region 2, are actually flipped, and this is a sign that the parallelization that it's doing is not correct. And finally, attempt 3, which is correct, is also doing parallelization and also has some events out of order. But in this case, the events that are out of order are the blue versus the yellow events, and this is actually not a bug. This is not a problem. Parallelization is happening correctly here. So in light of the fact that the events can be out of order, the question becomes, how do we check correctness? So to reiterate, out-of-order data may or may not indicate a bug in applications like this one. And this parallelization, additionally, parallelization for this kind of computation is challenging even for domain experts. We gave this particular computation to domain experts on the Flink user mailing list, and the second parallel solution that's wrong is actually the solution that was come up with on the mailing list. So it's not straightforward to parallelize these. And because out-of-order data may or may not indicate a bug, the question of checking correctness becomes, how do we specify correct ordering behavior? That becomes really the core challenge here. So what do we identify? What have we identified so far? So we want what have we identified before about the solution? We want the solution to be accessible to end users. That is, it shouldn't have any complex specifications or require any expertise about distributed systems and how they work. We also need to be able to accommodate a combination of ordered and out-of-order data, and that's crucial for the reason of, as illustrated by the example on the previous slides. And so these are our requirements for our testing solution. And for our solution, we make a domain-specific insight here, which is that we don't want to have a complex specification, but the stream processing domain is actually special in that we already have kind of most of a spec, and that is the sequential version of the program. So you've already written the correct sequential program, and the only question is your parallel program correct with respect to that one? And so that gets us most of the way of having a spec for free. And the only thing that's left is to specify what is the allowed ordering behavior. How can the parallel version differ in order from the sequential one? And so this is a very lightweight kind of specification that we'll go over briefly what it looks like. And an additional benefit of differential testing here is that we avoid false positives due to underspecification. This is just this is because of differential testing as approach in general. So let me say a little bit more about the specification language. So a typical scenario is that data is ordered by keys and unordered across keys. For example, here I have stream 1 and 2 possibilities for stream 2 that I'm doing differential testing for. And as we saw in the example, stream S2 is buggy and stream S2 is correct. And the way you specify the ordering behavior here is that events of the same region, in other words, blue events and yellow events, are ordered, so they shouldn't be out of order. But events of different regions, blue and yellow events, can be unordered with respect to each other. And the way you specify this set of allowed orderings is that you write a relation between pairs of events. So the specification takes pairs of events and returns a Boolean. Here are some typical examples of that. So events of the same key are ordered. That's the example we just saw. Maybe all events are false. This specification says that all events are unordered. This true specification says that all events are ordered. And finally, you can write more complex things, such as this specification, which says that events whose locations differ by at most 1 are ordered. And the differential testing problem then becomes, are these two streams, S1 and S2, equivalent up to reorderings allowed in the specification? So the technical challenge here is checking equivalence of two streams. For example, I have stream S1 with these events, stream S2 of these events. I feed them both to a matching algorithm, and I've also given the specification, which is for any pair of events, when are they ordered or not, and then my matching algorithm has to decide are streams S1 and S2 equivalent up to the reorderings given in the specification. And an additional challenge here is that the streams might be very large. You want to test the system under real data or under load, and so you want to be able to handle real input workloads. The naive solution would be to store the entire stream S1 and the entire stream S2, and then just compare whether they're equivalent up to the reorderings. But this is very inefficient. So the question is, when can I drop events, basically? I have some events from S1, some events of S2. Which events can I match and drop and say that I don't need to worry about these anymore? So the equivalence algorithm that we design, in order to accommodate a large amount of data and produce a verdict, we want to design an online algorithm. So it should reach a verdict as soon as possible, and it should use minimal space. And in the paper, we're able to show an optimality theorem, which is that the algorithm that we provide uses minimal space in the sense that any other correct algorithm uses at least as much. And we also discuss what are the bounds that you can get on space usage in practice if you just look at specific scenarios, specific specifications, and input stream and streams. So for a discussion of that, please see the paper. To briefly explain the experiments that we did a series of 4 case studies to try to apply DiffStream to finding bugs in applications. And so the first 2 case studies are looking at particular Flink applications. The first one being an aggregation over taxi GPS data, and the second one being parallel topic counting, as we saw in the previous slides. And then second, we looked at applying it to existing benchmarks. So we looked for existing benchmarks that we could test it on. And for this, we actually adapted MapReduce programs because those are much more commonly studied, and so there is a good existing work that we can existing benchmarks to look at. And what we show for these MapReduce programs is that, in contrast to prior work, differential testing as an approach avoids false positives. And finally, we looked at what is the overhead of this whole framework. So what is the cost of deploying it? And we find that over just running the applications themselves, we have only a modest 5% reduction in maximum throughput. So to say a little bit more about one of the case studies, for the MapReduce case study, what we did is we looked at this paper from ICSE 2014, which did a study of production MapReduce jobs, and in particular production reducers, user-written reducers. What they did is they looked at 507 production jobs, and they identified that actually a lot of custom reducers written by users are non-commutative, meaning that the output of the reducer depends on the input order. And the problem with that is that a lot of existing work tries to test reducers for commutativity, and so it will actually result in a false positive on these non-commutative reducers. So basically, for 58% of these reducers in custom production jobs, existing work has a false positive. And the diagnosis, if you think a little deeper about it, is that existing work kind of underspecifies the program behavior. In particular, it underspecifies the input behavior. So this is what results in the fact that the reducers are non-commutative. And it underspecifies the possible orderings that may occur. Underconstrains the possible orderings that may occur. So what we show in the paper is that this is actually a clear advantage of taking a black box approach with differential testing. So we are able to detect 5 out of the 5 true positives that we of MapReduce programs that we write in Flink, and we're about able to avoid 4 out of 4 false positives at the same time. This is a very rich space with a lot of opportunity for future research. Our broader goal here is to make distributed programming over data streams, for example, in stream processing systems such as Apache, Spark, Flink, and Storm, more reliable by eliminating bugs due to unexpected behavior in the presence of parallelism. And there's been a lot of interest in related domains, but this particular domain has not been very well studied, and it's not a solved problem. So for example, MapReduce has been widely studied, where you look at commutative and associative aggregators. Static verification is a set of approaches that look at the verification of distributed protocols and systems, but are not directly accessible to end users of, for example, stream processing systems. And in this work, we looked at just a particular kind of bug, which is bugs due to out-of-order output, but we didn't handle other kinds of bugs, for example, in a setting where you have faults or approximate computations. And so this is a rich space for future research. In summary, I have presented DiffStream, a differential testing library for testing streams in distributed stream processing systems up to lightweight reordering specifications. And DiffStream is online, it's optimal, and it's effective and low overhead in practice.